So next discussion would be on the, so in the discrete scenario we have seen the how to, we have found out the um, mean and expectation in mean in terms of the expectation and the variance. So we try to show for the continuous scenario how we can find out the expectation values and the variance in a continuous form. So the formula in the, I'll just write the formula side by side, be easy to understand. A similar formula, but just for the using the integration, we are writing this. So it will be like e of x, ei into xi, that discrete scenario. And for the variance formula would be same, e of x square minus e of x whole square, where e of x square is summation pi into xi square, right? So this xi square and xi was there. So the probability multiplied by this number. Same thing we are doing here. And as we to plus infinity, fx multiplied by x dx. Same like this. So x multiplied by fx. So whatever variables you got, you are supposed to multiply this with x. That's it. And for the ex square, the same integration will become fx multiplied by x square dx. If it is, let's say, in terms of t, it will become a t square for this t. So same, basically, it's the same things we are doing here. Just extra x and x, I mean like x and x square, same as what we had used there. We are using. Let's take an example. You'll understand better. Means the example. So let's take a function fx by 4 minus x 7 x minus 3, where x is between 1 and 3 and 0 other, right? So let's see, this is a certified PDF. We do not need to check it is as a PDF or not. So how can I find out the x for this case and variance? So for this, as per the formula, x multiplied by fx dx. Now since x between 1 and 3, change it to 1 and 3. So 3 by 4. So it is 3 by 4 outside because it's a constant value. Let's take 3 by 4 outside. This 3 by 4. So it will become x multiplied by 1 minus x multiplied by x minus 3 x. Let's multiply all this. X minus 3 minus x square plus 3x dx. So it will be 4x, right? 3 by 4, 1, 2, 3, x, 4x minus x square minus 3 dx. Multiply this 3 by 4 will become 1, 2, 3, 4x square minus x cube minus 3x dx. 4x cube by 3 minus x to the power 4 by 4 and 3x square by 2. 1, 2, 3. So eventually if you just solve this, so this is your mean. That's how we should find out the mean for the continuous variable. What about the variance? The variance, first obviously we need to calculate the ax square. 1, 2, 3 square fx dx. Of course, I'm not writing this same thing again. Typically, I should write minus infinity plus infinity x squared fx dx. Then I should write minus infinity plus infinity everything. Same, right? So let's now multiply it by x squared. Same process, multiplications will change to the x. 4x minus x squared by 3 dx. So 3 by 4, 1, 2, 3, 4x cube minus x to the power 4 minus 3x squared dx. So 3 by 4 integration would be 4x to the power 4 by 4. So on x to the power 5 by 5 and 3x cubed by 3 again go 1, 2, 3. So we solve again this, it should become something like this. So now the variance of x would be a of x square minus a of x whole square. So 21 by 5 minus 2 whole square. So eventually it will be 1 by 5. So the meaning as if like in terms of the area, standard mean concept like around this particular number, particular continuous value we have, and this is the variance number. So from the mean this much on average you are away from this particular part. So that's how basically you have to calculate the mean and the variance for the continuous variable. So we have found, we know that how to find out the PDF, how to check that it is a PDF. Then we can find out how we can find out the CDF, and given a CDF, how we can find out some in interval kind of scenario, the interval kind of greater than less than, any kind of interval scenario is there. From that, how we can find out the in between numbers. So typically, like from this set, how these numbers are there in between, so we can find out using CDF. I will see its application later when we will talk about the normal distribution. So basically, next part is distribution. So that is the scenario. And finally, we know how to find out the mean and the variance of the standard deviation for both discrete and the continuous scenario. So this is the standard procedure. Now, obviously, there are a lot of applications are there, a lot of probability density function, probability distributions are available. Now, people try to formulate certain kind of a problem in terms of the something is called the distribution, probability distribution function, and we found out certain type of probability distribution function which are quite popular. So we defined those distribution functions in certain ways, and then we've modeled those distribution functions either from the discrete side or from the continuous side. So that using those models we can find out the expected probability, unexpected values. Not every point of time we are going to do that experimentation. So basically, suppose there are n number of a kind of random experiment can happen. On those random experiment, we can categorize those random experiment in this kind of a standard experimentation purpose. So, like given that there's such kind of suppose we are tossing say 5 coins, so we are going to tell that okay, this tossing a particular coins can be modeled as something as called binomial distribution because of certain reasons. So we tell that. So okay, so from then since it is similar to this kind of a scenario, we are going to use the binomial theorem model to find out the certain probability. Right? So this is the process we generally try to fix this particular area. Of course, any point of time, given that a situation, you cannot go and do an experiment on the basis of that whole structure. So it will be quite a uh, tough thing to do. So in our discussion, we are going to add few standard distributions. Of course, both the cases, of course, we are going to learn more about the discrete, but the maximum impact is the further continuous. So the if I say the probability distributions. So we got again discrete and continuous. For discrete, we are going to look into the uniform distribution, binomial distribution, and the Poisson distribution. These distributions are most popular distributions, and in this case, we are going to see the normal and the standard normal distribution. Same, almost same. So this is the most impact, though discretes are quite easy to understand. And of course, there are a lot of applications are available for this discrete models. So we'll see this one by one and try to understand which particular area we can use this kind of problems. Let's start with the very basic one, that is the uniform distribution. Probably the easiest and the simple distribution. So uniform distribution means is that every this is by the way this is a discrete distribution, as I told, this is a discrete. So suppose if there is n observations are there, each observation has same probability. If that is the scenario, you can tell that distribution as a uniform distribution. You can tell okay, if I toss a coin, unbiased coin obviously, I'll get either head or tail, both has same probability, uniform distribution. I throw a dice, I'll get 1, 2, 3, 4, 5, 6 with the equal probability, that is 1 by 6 each. That is also uniform distribution. So this is the simplest distributions. So if it is a typically in normal sense, if I just try to write, if you got the x variable with the probability, if there is a n distributions, that is x1, x2, x3 till the xn. Since there are n distributions, that means that each and every observations are going to get, or random variables are going to get same probability of 1 by n. So that obviously at the end it has to be 1, and this 1 by n is non-negative numbers. There should be more than 0 or more than. So this is the uniform distributions. Of course, can find out the mean. So basically, as a parameter, if we know the number of observations, know the number of random variables, that is good enough to construct this particular distribution. Of course, we need to know the numbers, as it like for the dice it is 1, 2, 3, 4, 5, 6. But I mean, like depend on what are the values you are going to put. But probability part, we know mean obviously. Um, summation of I want to n I into xi. So since it is in everywhere with xi, so it will become standard mean equation for the normal distribution. So uniform distribution is looks like a same our old mean distribution equation, right? So typically in that deterministic situations, what we do actually, we feel that all these x are nothing but equally probable. That's why the same equations actually we are going to get. So uniform distribution is as if when we are talking about a discrete scenario, it is nothing but that we are giving equal weightage, equal probable to all of our observations. That is the meaning of the this deterministic sense. So of course, we are saying if x can take a value, we had done this case before also. Let's say in, right? So what we had, so summation of 1 plus 2 plus 2 n. So remember the formula n plus 1 by 2. So the expectation of x would be 1 by n multiplied into n plus 2 is n plus 1 by 2. So we had done this before. Expectation of x would be n by 2. Similarly, if I go for the x variance part, e of x square would be summation n pi to xi square 1 by a x square. So we have to do this same for the 1 to 3 and all. So if you remember, that was the formula was 1 by n. So 1 to 3, n into n plus 1 to n plus 1 by 6. So it was n plus 1 to n plus 1 by 6. And eventually the variance. We had done this. That plus 1 to plus 6 n plus 1 by 2 whole square. So n square minus 1 by 2. So eventually this is the process, like this is a simple distribution to talk about. So this is the uniform distribution, simplest. Second one is called the binomial distribution, the most popular. So binomial distributions, of course, a lot of things are there, but I'm not going to tell a lot of the details about all these things. So typically it comes from something as called the Bernoulli's experiment or Bernoulli's series kind of situation, where we define any experiment, any random experiment. In this particular case, the random experiment or the random variable, they call it as a trial. On the particular trial, it could be only two options. Either it could be a success or it could be a failure. So probability of success can be anything, and probability of failure would be 1 minus that probability of success. So if that is any kind of practical example, any kind of experimentation, if you can define like this, then you can use this binomial distribution or Bernoulli's experimentation, or on that basis you can use the binomial distribution. So I can write like this way when you should use this. So one is a result of any trial can be classified as only two categories. So that is the success and failure. So failure would be 1 minus of the success. Second assumption would be probability of success in each trial has to be remain constant. It cannot change in each every trial. And third is all the trials are independent. If these three things follows, then generally we tell that okay, this is going to follow the. I mean, we can model this particular scenario in terms of the Bernoulli, sorry, in terms of the binomial distribution. So um, your distribution uh, depends on, so this distribution depends on two parameters. We are introducing the word parameters, so later we'll talk more about the word parameter in the sampling and all. So the parameter are n and p. Basically, n is the number of observations and p is the probability of success. Right? But if this is the two parameters are there, then the PMF, since it is discrete, the PMF for binomial distribution is given by x is equal to ncx e to the power x 2 to the power n minus x. So where this q is nothing but the probability of failure, that is 1 minus probability of success. And x can take value of 0, 1 to not a negative value, 0 to n. Now if we just expand this in terms of a PMF table, if it's or the p 0, 1, 2 like this till the n, so we put 0, so it will be nc0 p to the power 0 q to the power n. So typically is q to the power n. 1 nc1 p to the power 1 q to the power n minus 1, and nc2 p to the power square q to the power n minus 2 and so on. Finally, it will end up with the p to the power n. So if you see this, and if you remember, as per my definition, if I add this numbers square n minus 2 in this p to the power n, it should be 1. Let's see, it is happening or not. So if you see this, observe this, this is nothing but a binomial expansion equation, right? So this is nothing but, if you see q plus p whole to the power n, that is the expansion of, if we expand this, you will get this terms. So basically on the basis of this particular model, we are following this. And of course, since q plus p, as I told, q is equal to 1 minus p, that means that q plus p is equal to 1, so it's 1 to the power, that is eventually 1. So which is following our um, basic definition of the being a PMF. So this equation can be a PMF, and any number in between this particular series can be given by this equation, the binomial series equation. So from there we can find out the probability on the basis of the number of observations and the probability of success. From the probability of success, of course, I'm going to get the probability of the failure. Of course, since the model is there, we got the PMF. That means that we can find out the mean also. Traditional way to find out the mean, that is E of x would be summation pi into xi I into n. So of course, a lot of calculations are there. Not going to do that particular calculation. If you do all the calculations, you'll find out the mean would be given by n into p, right? And the variance will be given by n p q. Of course, standard deviation would be the square root of this. So this is the, like, again see, if I know the parameters n and p, I can find out both paths. It's nothing but n p, right? So I can find out the mean and the variance for this particular case. Also, other way also it is possible that I can say that, okay, if I know the mean and variance, since there are two unknown variables, I should find out the n and p also. Like that also, I mean, can take the secondary kind of a parameter wise. Like if you know the mean and variance, you can actually construct the equation, construct the PMF. Anyway, let's see some practical examples where we generally use this. So I've always remembered that model, whatever experimentation we are going to describe, that can be modeled as a kind of a probability of success and the failure. Initially, what I have wrote, that three basic things should be followed into that particular experiment. If that is a get followed, we can find out the that kind of it is properly getting modeled by that particular assumptions. We can take these numbers and we can find out the parameters in terms of this equation, in terms of this experimentation. So first example, simple one. Coin is a mover. So 3 coins are tossed. Find the probability. This type of problems can be calculated in multiple of zero heads, one head, two heads, and three heads. And there's more than one head. And there's at least one head. Like, so look, I mean, definition wise, if I can model this in terms of the Bernoulli's principle, this is good enough. So how can I define this? P can be kind of a as if success of every trial. So what is the success here? Success of getting hit in every trial. So see, observe, I am defining the success here in terms of getting hits. Possible. So that's how basically first scenario is done. That okay, I can. So if there could be success of getting hit. If you are not getting hit, then it is failure. So I can model the experiment on the basis of this. Second is that the probability of getting hit won't change because, as I told us, success ratio, success probability should be constant all over. So that is possible. It's happening here. And third one is the getting a head on the first toss does not depend on the getting a head on the tail on the second toss. So it is a independent event. So it is following the situations. That means it can be modeled as a binomial distribution. So the success is here. minus half. For this case, if it is not, like since it is an unbiased coin, obviously I'm writing half. It can be anything, any number. So if it is a biased coin, I can still make this as a binomial distribution problem because it has to be success and failure. It has nothing to do with the 0.5 or it is 0.2 or something like that. So Q would be 1 minus half, that is half. And N is given that number of independent trials. How many trials are there? 3 trials are there. So if I want to make the EMF, so Cx q to the power x, q to the power n minus x. So if I just put the numbers 3cx half to the power x half to the power n minus, that is 3 minus x. So divide 3c 3 3cx half to the power 3. So it is constant. Like since the probability are both the same, so half to the power 3 is constant. Now, what is called that success x is equal to no hits. So 0. X is equal to 0. 3 is 0 half to the power cube. That means 1 by 8. Right? X 1 hit. Because x is equal to 1. That means 3c1 of cube. That is 3 by 8. If x is equal to 2, is 2 heads. That is x is equal to 2. That means 3c2 of cube. That is again 3 by 8. And it's 3 heads. Sorry, 2 heads. So this is equal to 3. 3c3 of the power cube. That is 1 by 8. Yes, you can find out. Second one, probability x is equal to more than 1 head, that more than 1 success. So if it is more than 1 success, that means px is equal to 2 and px is equal to 3. That's the more than 1 success. So eventually from there we can take the numbers. 3 by 8 is 1 by 8. That's half. And third one is at least 1 head, that is at least 1 success. That is 1 minus p of at most 1 success. This 1 by px is 0. So from there, so 8. So by 8. Like this. We can use a simple scenario based binomial distribution. Now let's make this a little bit complicated. So let's put this expectation into this. Okay, exact expectation. Anyway, let's put this. So say 5 points are tossed 3,200 times. Find expected frequencies of distribution and mean and ST also. So 5 coins are tossed. Of course, we know the fx could be 5cx of the order 5. So This is not change anything. So depending on how many heads we are going to get as per the success, let's write down 0, 1, 2, 3, 4, 5. This is only half to the power 5. Just putting the x value here. 5c1 half to the power 5, 5c2 half to the power 5, 5c3 half to the power 5, 5c4 half to the power 5, and finally again correct 0 to 4, not 5. 5. And now how the distribution would look: number of heads, number of tails, the probability. Now this is the probability expected returns. 0 head, that is 5 tails. Do I need to put other? 5 should be there. Yeah. 10 up to the power 5 will be there. 0, 5, 0 heads, 5 tails. That means probably it is 1 by 32, 3200. So this multiplied by 1 by 32, that means that we are supposed to get 100. This case 1 to 4, 5 by 32, same do, should get 500. 2, 3 again, same 5c2. So this is 10 by 32. So we got a 10,000, sorry, 1,000. 32, same 10, 32, 1,000. 4, 1, 5, 32, 500. Eventually, 5, 0, most grateful. But here's the distributions would look like in terms of the number of hits or the number of tails. Mean forward already I know the NP. So N is 5, N is half, so 2.5, and the standard deviation would be root over of NPQ. That means 5 half half. So root over 5 by 2, somewhere in the other one. Straightforward, simple. Last problem, the binomial distribution. So in 10 indent. So of the effective time probability that an even number will appear 5 times is twice the probability that an even number will appear 4 times. Find the probability that an even number will not appear at all in 10 independent throw the dice. Okay. So the thing is that it is trying to tell that the 10 independent throw we are doing, dice is effective, but you can say that a even number will appear 5 times, right, in the 10th row is twice of the probability of that an even number will appear 4 times. Okay. So basically, in a single set of experimentations, it is trying to find out the connections between these two. Of course, from there we can find out our parameters. At the end of the day, I need to find out the NNPA. Otherwise, I cannot construct the parameter and construct the distribution. So that is the scenario. So again, we can model this experimentations since it is a dice problem. So probably problem of even getting even number is my success. Probability of not getting even number is my failure. I got a finite number of trial here. That is 10 trials are there. Since I can find out these two situations, that means that I can definitely construct this problem statement in terms of the um, binomial distribution model. So let's define this probability of success, that is getting a even number. It would be probability of failure, that is getting an odd number obviously, but it's not important. Actually, not even number. That right? N is number of independent child. That is number of throws. That we know. N. P and Q do not know. Since it is defective, we cannot tell. 10 CX P to the power X Q to the power 10 minus X. Good enough. Now what is given? That in this particular scenario, getting a even number 5 times is twice of the probability getting a even 4 times. That is given. So let's find out x is equal to 5. Is it 5 if I just write 10C5 e to the power 5 q to the power 5. A4 would be 10C4 e to the power 4 q to the power 6. So let's use this. So 10C5 to the power 5 q to the power 5. 10C4 to the power 4 q to the power 6. Right? So can I write the So how can I write like this and this? So let's expand this 10 factorial by 5 factorial, 5 factorial, e to the power 5, q to the power 5, 10 factorial, 4 factorial, 6 factorial, e to the power 4, q to the power 6. Of course, one side it will be p, one side it will be q. So let's first now this 1, it will be p, so it will be q. So here 5 factorial means 1 by 4 factorial divided by 5, and 5 factorial is there. This side 1 by 4 factorial, let it be multiplied by 6 factorial is 6 multiplied by 5 factorial. So 5 factorial gone, 4 factorial gone, right? So it will become 2 by 5, 2 by 6. So that means 6p is equal to 5q. Oh, sorry, I missed a 2. This should 2 multiplied by this 2. Okay. So this is there, this is there, this is there, so this is 3. So 3p is equal to 5q. So if it is 3p is equal to 5q means 1 minus p. So 5 minus 5p. So 8p is equal to 5. So p is equal to 5 by 8. So we got the quantity. Q would be 3 by 8, obviously. So now the fx looks something like this: 10cx 5 to the power x 3 to the power 10 minus x. Right. This is the formula. Now, what is expected at 10? So there should not be an event. Even number should come. So I mean that is x is equal to 0. There should not be any success. Just put the value 10 is 0 by 0 to the power 10. Eventually, this is okay. But one number is that's how basically we need to deal with this kind of problem. So this is the meaning of the binomial distribution. Now, many cases it happens that we do not have enough data. If you are dealing with data science in many cases, you will see that we do not have this amount of data. Only probably we can manage the average value of the practical cases. So if that is the kind of situations are there, then one specific type of distribution, which is kind of a modified version of the binomial distribution, basically that is called the Poisson distribution. If the data is limited, typically this we can actually find out. You can prove if you can want to see. You can consult the book that we can derive these Poisson distributions PMF from the binomial distributions equation. So, what is the assumption here? That when binomial distribution has n very large but the probability of success is very less, but NP is finite, then binomial distribution is become Poisson distribution. So your observation or your number of trial has to be a lot. It's a huge number should be, and the P is the probability of success value is quite low. But in the point of time, NP should be some finite number. If that is a scenario, then we can optimize or we can approximate the binomial distribution into the Poisson distribution. So here for this binomial Poisson distribution, the equation given by the PMF given by fx to the minus lambda to the power x by x factorial, or x can take value same as the value. Well, lambda is positive, and this is the e. Of course, you know that is a standard exponentially. Lambda is a positive, and this is a parameter where mean, variance, both for this case is the lambda. Basically, the parameter itself is the mean and the variance, which is nothing but actually this n into p. If you compare this to binomial distribution, let's see some example. Business firm receives on an average 2.5 telephone calls per day during 10 a.m. to 10:05 a.m. Find the probability that on second day the firm receives one is no call, or number is exactly 4 calls in that interval. So, of course, from the structure you can see that there is a very less data is there. Of course, there previously, at least for normal problems, you can find out the number of trials, number of probability of success. These things are of finding these numbers are possible, but in this case, only you have this number, that is on an average you are going to get a 2.5%. Let any practical scenario wise you find out this kind of numbers are only available, rather than there are not much experimentation data are available. If there is a data insufficiency or this kind of scenario, but still you need to make a model, then this is the model you should use, that is the Poisson distribution you should use. So, of course, from there you can understand that you got the lambda on an average of 2.5 calls per that particular minute. So, this is the parameter I got. So, equation would look something like this. It will become minus 2.5 for 3 over x divided by x factorial. This is your PMF. First thing is no pulse should be there. It means x is equal to 0. So once 2.5 1 to the power 0 by 0 factorial. This is 1, this is 0. So string a to the 0 is 1. Factorial 0 is also 1. So final answer is a to the power 2.5. What number it is? This is the number. Second is exactly 4 pulse. X is equal to 4. So that means e to the minus 2.5, 2.5 1 to the power 4 by 4 factorial. Again, to simplify this 0.336. So that's how basically, once you understand the parameter, it is quite easy to handle this kind of problems. Let's quickly do two more. So let x be the distribution follows Gaussian distribution if x is equal to 1 is equal to 2, x is equal to 2, the things happens like this, then what is x 0 or 1 and expectation of x. So basically, eventually we just find out the parameter or the e of x. So what is given? Ex is equal to 1 is equal to x is equal to 2. So quite straightforward. Just put in the equation 1 by factorial 1 lambda square by factorial 2. Both are non-negative, gone. So lambda is equal to lambda square by 2. That is lambda square minus 2 lambda is equal to 0. That means that lambda can be 0 or 2. Of course, 0 does not mean nothing. So of course, we are going to deal with the 2. So lambda is equal to 2. So already I can tell that expectation of x, that is the mean, that is nothing but lambda, that is nothing but 2. So next is x is equal to 0 or 1. Or means addition. Since there is no overlap, so there won't be intersection thing. 0 or 1. So now it is lambda 0 by factorial 0 minus lambda to the power 1 by factorial. So factorial 1. So it will become lambda minus lambda plus minus lambda into lambda. Right? So let's put the values. Minus 2 plus 2 minus 2 multiplied by 2. So 3 to the minus 2. Whatever number it is the answer. So it may come into the mind, what if some problem only uh, that is quite confusing, that I should go for the binomial distribution or I should go for the Gaussian distribution, because I know that lambda is equal into p. From there I can actually estimate the value. So given that it is a quite small number, let's see how much error generally we do by doing a same problem in terms of the both equations Gaussian the binomial distribution. Okay. Both. Certain toy company times that average number of defective items 10% on an average. What's the probability of getting exactly three defective items in a sample of 10 defective items? Right? So we can do this in terms of two problems. One thing is that I can tell that okay, so since number of observations are 10 and probability is given as 10% is 0.1%. So I can find out lambda as n into p, that is 10 into 0.1, that is 1. So the F3 can be written as e to the power minus lambda, lambda 3, 3 factorial, that is e to the minus 1, 1 to the power 2 by 3 factorial, so 1 by 6 into e, that is 0.061. Right? Now, same problem I can model in terms of the binomial also, because already I know n is equal to 10, p is equal to 0.1. So I can construct the binomial also. So for the binomial, we can see 3, 1 to the power 3, and 0.9 to the power 10 minus 3, 7, 10 to 3, 0.1 to the power 3, and 0.9 to the power 7. Same. I will like same problem, two ways. So, and 0.57. Right? So, see, there is a language difference between these two. Of course, for the same amount of observation or trial, uh, this should be more accurate, obviously. The binomial should be more accurate, but eventually, if, as I told, if n goes quite high and p goes quite low, 10% may become a 1%, and n becomes 1,000 or 5,000 out of say 10,000, if I'm getting a 1% chance of getting some effective items, then this would be the perfect way to estimate that scenario. Because obviously, because the number is quite low now, this then will become. So basically, this is the process of discrete probability distribution systems. So we got three probability distribution systems for the discreteness, that is uniform, binomial, and the Poisson distribution. So we discussed a little bit about all these three distributions, and we have some examples for all three distributions. Now, of course, as you can see that okay, in many practical scenario, even if in your research also you'll find out a lot of practical scenarios where you are going to use these distributions. But of course, the continuous distribution, that is the normal distribution, that has the maximum impact and probably. So we'll talk about the normal distribution in the next class, and we'll see that eventually that normal distribution concept will um, flow to the next discussion, that is the sampling theory, and later it will go to the hypothesis theory and a lot of places. So basically, that is a kind of a distribution which has the highest impact in terms of the applications in many places. So we'll stop here with this discussion. So I have already mailed you regarding the books. So I believe those books are quite simple to understand. So you can see all these things are there. If you want to read about this particular part, you can find out it in DAS as well as JK, JK. So first two books basically you can find out. So Ross could be a little bit more towards the probabilistic scenario. So if you want to learn more about the probability, later next class we'll talk about Gilbert joint probability, conditional marginal probability, all these things. So there the Ross would be good enough. But otherwise, this till this the first two books would be good enough. So, yes, refer. Okay, that's it for today. So if you have again, if any questions, please let me know. If you have not find out the assignments, please again let me know. Mail me if you have not got this, and if you have got the assignments, please make sure that you submit on time so that we can be on the schedule and we can share the next assignment as per that timeline. Okay. Okay, that's it for today. Thank you. If you have any questions, you can ask now or you can mail me. Great. Thank you.